Hello, good morning. Welcome back again to the second part of the reading session. The title of article is Randomly Coupled Multi-Core Fiber Technology. So in previous session, we have seen that this invited paper explains about a new kind of fiber technology that is called random coupled multi-core fiber. So random coupled multi-core fiber is a technique where within 125 micrometer of cladding diameter, number of cores are more, they are spatially distributed. So that is why it is called multi-core. But this multi-core provision can be facilitated in different ways. One is called weakly coupled, another one is called systematically coupled. So these are the two separate, distinct provision of distributing multi-core in the cladding region, 125 micrometer standard cladding diameter. So far as this randomly coupled multi-core fiber is concerned, it is intermediate of these two, weakly coupled and systematically coupled. Why there is need, or why we go for randomly coupled multi-core fiber? What this paper is telling that we can achieve two advantages simultaneously in the randomly coupled multi-core fiber. What are those two? That is the higher spatial channel density, means number of core may be more, as well as ultra low transmission loss, very less transmission loss. So these are very interesting features. This number of core can increase, as well as so-called losses, intermodal, so mode dependent loss or modal dispersion, or say non-linear effects, which occurs if we increase the number of cores and coupling is more, systematic coupling, say for example. But here, if it is randomly coupled, they are telling that transmission loss is less, as well as we are increasing the number of cores. Why? Because this randomly coupled provides a suppressed accumulation of modal dispersion, number one. Number two, mode dependent loss is suppressed. And number three, the non-linear impairments are also suppressed. So these three, of course, these are the reason behind why randomly coupled multi-core fiber is giving higher spatial channel density as well as low transmission loss, because without addressing these three issues, that is the modal dispersion, mode dependent loss, and non-linear impairments, without addressing these three, it is very difficult to achieve the advantage. But this article suggests that these are the reason why in randomly coupled multi-core fiber, density of cores is increased as well as transmission loss is decreased. So as a state of art, random coupled multi-core fiber can accommodate 4 number of cores, 7 number of cores, or 12 number of cores in a standard 125 micrometer cladding, while achieving no transmission loss and small modal dispersion. So in last session, we have gone through this introduction part, and interestingly, this article suggests that many researchers have already demonstrated the effect is in randomly coupled fiber. There are 6 articles, I think is 7 articles basically. In this, you see here 14 number 2, 20 number, these 7 articles. which has been cited in this article, demonstrate about the suppression of accumulation of modal dispersion in the randomly coupled fiber. So readers are encouraged to go through to understand how randomly coupled fiber is suppressing the accumulation of modal dispersion. Second feature, in order to understand how randomly coupled multicore fiber is suppressing mode dependent loss, that is MDL, has been addressed or demonstrated in the reference number 20 to 25. It means there are 6 articles. And third one, that is the nonlinear impairments, has been addressed in reference number 24, 26, and 27. So 3 articles are there. So whatever claim is there, the claim is that randomly mode coupled multiple fiber gives the advantages of suppressing the accumulation of mode dispersion, mode dependent loss, as well as nonlinear impairments. And beside that, the transmission distance, optimization of the transmission distance, as well as the wide band transmission in multi-core fiber, where randomly coupled arrangement is there for C band as well as for C plus L band in the reference number 30 and 31. So after that, it has been explained what are the content in different sections. Like section 1 describes about basic definitions, classification. Section 2 discusses about the multi-core fiber designs to assure random coupling and effect of fiber bends, group delays. Then section 3 describes how to characterize randomly coupled fiber, multi-core fiber. And section 5 reviews the connectivity technologies for splicing and termination of randomly coupled multi-core fiber. And then section 6 reviews the multi-core fiber amplifier technologies applicable to randomly coupled multi-core fiber amplification, because there is a need of amplifier also. If multi-core fiber is there, then after a span of say 50 to 80 kilometers, we need multi-core amplifier also, so which should be compatible with the fiber arrangement. So that has been reviewed in section 6. Section 7 describes transmission experiments over randomly coupled multi-core fiber and shows the performance improvement in nonlinear transmission, and also discusses suitable applications for randomly coupled multi-core fiber. And section 8 concludes this article. So this is very interesting article so far as new technology is concerned, that is the randomly coupled fibers, multi-core fibers. And with the obvious interest or in terms of advantage is that it suppresses this randomly coupled multi-core fiber, suppresses the accumulation of modal dispersion, reduces the mode dependent loss, as well as reduces the nonlinear effects in the multi-core fiber. So now let us move to section 2, which is today's topic. So we will read line by line to understand it nicely. So the section is multi-core fiber classification. How to classify, what are the different types of multi-core fiber, including randomly coupled. So multi-core fiber can be divided into weakly coupled multi-core fibers and strongly coupled. So there are 2 types. Broadly, it is 2 types. One is weakly coupled and another one is the strongly coupled. So weakly coupled multi-core fibers are multi-core fibers where the crosstalk between crosses well suppressed, so that each core can be used as an isolated individual spatial channels and is compatible with the conventional transceiver for single mode fiber. So in weakly coupled multi-core fiber, the distance between these 2 cores are sufficient enough that crosstalk is minimized. and they can be treated as isolated individual spatial channel, and which should be compatible with the conventional transceiver or single mode fiber. Whereas strongly coupled multi-core fibers are multi-core fibers where crosstalk or coupling between cores is not negligible. There is a sufficient coupling. There is a sufficient crosstalk. That is very interesting to see. Even when there is a crosstalk, how this is going to decrease the mode dependent loss. So there are no clear numerical criteria to distinguish weakly coupled multi-core fiber from strongly coupled multi-core fiber. And the same multi-core fiber may be weakly coupled for a short range transmission and strongly coupled or multi-core fiber for long haul transmission. So now it says very interesting thing that there is no numerical criteria. So same fiber having same fiber structure, the multi-cores are there. For short reach, it may behave as a weakly coupled, and for long haul transmission, it may behave as a strongly coupled multi-core fiber. That is very interesting. So, which creates more curiosity. So, weakly coupled multi-core fibers are often referred to as uncoupled multi-core fiber or simply multi-core fiber. And strongly coupled multi-core fibers, coupled multi-core fiber or coupled core multi-core fiber or coupled core fibers. So there are different names. Simple multi-core fiber which are isolated, whereas strongly coupled arrangement is called coupled multi-core fiber or coupled core multi-core. So there are various names. Now let us go to next section. Increase the size for the benefit of better visibility. Now, strongly coupled multi-core fiber can be further divided into systematically coupled multi-core fiber and randomly coupled multi-core fiber. Now we can see this RCM, randomly coupled fiber RCM, comes into this category basically, strongly coupled. Now, strongly coupled is divided into two parts. One is called systematically coupled and another one is called randomly coupled. Systematically coupled multi-core fibers are multi-core fibers with the most strongly coupled cores. When multiple cores are located sufficiently close, the multiple cores act as a single microstructure multimode waveguide system. The eigenmodes of this coupled waveguide system can be approximated by the superposition of the local modes of individual cores, hence called supermodes. So since a strong coupling is there between this and this, so whatever resultant mode will be created, that is called supermode, and this occurs in systematically coupled multi-core fiber. In ideal waveguides, the supermodes are equivalent to an eigenmodes, hence orthogonal and uncoupled. So they are orthogonal and uncoupled in ideal waveguides. For example, in a systematically coupled multi-core fiber with two identical cores, when light is launched into the local modes of one core, the power of light is sinusoidally transferred to and from the local modes to the other core due to systematic mode coupling. So it is telling that suppose this is one core, this is another core. So there is a systematic coupling between these two. At first start, light is there in one core, the second start, light is in the second, and so on. So there is a systematically sinusoidally coupling. However, if we think of this behavior on a super mode basis, light is actually launched into both of the two eigenmodes, that is even and odd modes, and the sinusoidal power transfer between the core is the beating between the uncoupled eigenmodes. In this article, we refer to multi-core fiber with uncoupled or weakly coupled supermodes as systematic coupled multi-core fiber after the systematic mode coupling between the cores. By leveraging the weakly coupled characteristics of the super mode, the mode division multiplexing using systematically coupled multicore fiber has been proposed in reference number 32 and 34. In actual systematically coupled multicore fiber, various longitudinal perturbation can induce mode coupling between supermodes, but such a mode coupling can be suppressed by increasing the propagation constant mismatch between the supermodes by increasing the mode coupling coefficient between the cores. Although the supermodes are weakly coupled in systematically coupled MCF, splicing misalignment and mode field mismatch at the fiber input and output can easily induce the crosstalk between the supermodes. Therefore, the MIMO DSP is likely to be necessary for this type of multicore fiber, especially for the long haul transmission. Now coming to randomly coupled multicore fibers are the another type of strongly coupled multicore fibers, which has coupling characteristics between the systematically coupled multicore fiber and weakly coupled multicore fiber. So which has been defined in 35 and 37. So this is in between. So in this coupling regime, that neither supermodes nor local modes stably propagates without modal coupling, but the modes and randomly coupled multicore fiber experience a strong and random mode couplings along with the propagation. Such randomly coupled multicore fibers can be modeled as a concatenation of uncoupled short section. Concatenation is combination of tandem. This connected with this concatenation of uncoupled short section with strong and random mode coupling between the adjacent section, such as the fiber modes in 23. Strong and random mode coupling can make each section independent of adjacent section. Thus, the standard deviation or the root mean square of accumulated differential group delay becomes square root proportional. Square root proportional to the propagation distance. The RMS mode dependent loss sigma MDL of a randomly coupled multicore fiber system is also square root proportional to the propagation distance when the RMS MDL is less than 1 degree. To be precise, the RMS MDL can be approximately expressed as given in this 21 to 23 is article. So sigma MDL is equal to square root of the sigma g square. L is the propagation distance, L is the coupling, sigma is the variance of mode dependent loss multiplied by the square root of 1 plus 1 divided by 12 within bracket 1 minus d minus 2 square sigma g square L by LC. And the equation number 1 can be approximated by neglecting this 1 minus d 1 minus d minus 2 square. So like this, where sigma g is the variance of the MDL in the uncoupled sections, L is the propagation distance, L is the coupling, and D is the number of spatial and propagation modes. The MDL's variance of MDL and sigma g are expressed in units of natural logarithm of power gain, which can be converted to RMS MDL in dB and sigma g in dB in decimal by multiplying 10 divided by natural log 10, that is equal to 4.34 respectively. According to Ho and Kahan, that is 21-23, 2 is sufficiently accurate for, that is equation number 2 is sufficiently accurate for practical purposes when this variance of MDL is less than or is equal to 33 dB for special D is greater than or is equal to 8. That is the 4 cores or more. Figure 1 shows the dependence of MDL growth rate on RMS MDL calculated based on equation number 2. The proportionality of RMS MDL to the propagation distance is sufficiently sublinear in a practical MDL range of less than 10 dB. So this is the equation, this is the figure. They are sufficiently, if it is less than 1, so it is linear. After that, this is increasing like this. With respect to increase in the RMS value of MDL, that is variance. And y-axis is MDL growth rate over propagation distance. So let us see, the proportionality of RMS MDL to the propagation distance is sufficiently sublinear in a practical MDL range of less than 10 dB. Although random coupling has to be compensated by bi-mode DSP, the resultant properties such as square root divided by sublinear accumulation of mode dispersion and mode dependent modal dispersion and mode dependent loss are beneficial to suppress the calculation complexity and outage probability of bi-mode DSP. That has been explained in 23, 38 and 39 section number. So now let us see this side. So you can see here table 1 summarizing the difference between the randomly coupled multicore fiber and other type of multicore fiber. So let us see this one, and after that we can conclude today's session. So this is a very important table. Basically, this table explains the gist of matter explained in the section 2. So that this is the column fiber type. Here strongly coupled multicore fiber and weakly coupled multicore fiber. So you see randomly coupled falls in the category of strongly coupled, but their characteristic is in between these two. So number 1 is the systematically coupled multicore fiber and number 2 is the weakly coupled multicore fiber. So characteristics of randomly coupled multicore fiber is in between these two extreme things. So here core pitch means the distance between these two cores from center to center is small in systematically coupled multicore fiber because strong coupling is there, and in weak coupling it is sufficiently large, this distance between. And in randomly coupled it is medium in between these two. Mode coupling, that is the crosstalk, here weak between supermodes, here in weakly coupled weak between cores, and here strong and random. So you see in strongly coupled these are talking about supermodes because the modes which is developing the resultant mode is a supermode, which is the combination of say the light traveling in this and light traveling in this. However, in case of weakly coupled, we are talking about cores. There is a weak coupling between this core and this core. Dominant source of modal dispersion and mode dependent loss is DGD, MDL between supermodes. Here both may affect, here DGD and mode MDL between cores. So DGD is full form, should be mentioned here, but somewhere else it will be there. Then proportionality of MDL to propagation distance, it is linear here. Here also linear, here square root or sublinear. So mode coupling between cores is strong and systematic, that is A here, deterministic, this we can determine. So we use the term systematically coupled in this paper. So this is all about section 2. It is telling about what is the major characteristics of randomly coupled fiber and where it lies. This classification of multi-core fiber, it can be divided into two parts, that is called systematically coupled, where strong coupling is there, and weakly coupled, where weak coupling is there because of larger distance between cores. So with this, let us conclude today's session. So we will meet soon. Thank you so much for attending this session.